final thing to wrap up with this chapter is to understand the word power. Okay, so power is very simple. It's basically how fast you are consuming the energy. Okay, more rigorously speaking, right? So that's the definition, is the rate of change of energy consumption. Okay, so in some sense, this is power consumed. You can talk about power produced. In that case, I don't think we'll talk about that much, but in this chapter, but maybe in 3B, you will talk a little bit more about power plants production, how do you produce power, but in that case, you just change this word of consumption to production. So how much energy, production, how much energy, what is the rate of change of that, of the energy production, okay? So what does that mean? The moment you see rate, you understand, P will stand for power, you understand it's ddt, right? Rate of change translates to ddt, so how much time taken for the energy, whether consumed or produced, okay? So this also tells us there's the concept of average power and instantaneous power. So average power is defined as the change in energy over the change in time. The instantaneous power is just take that limit to 0, okay? So why is this useful? So you can talk about, for example, what is the power you need? So this is basically how fast you can do something, how much energy, if you think this is easier to interpret, that's good. How much energy you can produce, or you can consume, or you can use within a given time. Okay, so let's say you need to. Let's say you need to. Let's see if we can find an example. If you can, yeah, if you want to raise an object, right? Let's go from here to here, right? Should we go on a slope, or should we go? Let's go vertically, just to keep things simple first. Okay. So if I want to raise a block of our favorite number, 5 kilogram, up by, let's say, 10 meters this time. Okay. And if I can do that with in 2 seconds compared to 4 seconds, which one has more power? So that's one way you can use it. So all you have to do is figure out what's the energy change, what's the change in energy. So to move it from here to here, you need to overcome gravity, which the change in energy is mgh, or mg delta h, right? So we have a 5 kilogram, g, let's use 10, so I can do mental math. H is 10, and the change in energy is positive. So that's fine. So that can be positive because the displacement is positive. Again, I'm going to use y over here. So I have 100, so 500 joules. Okay, and if I do that if I'm doing that in 2 seconds, now because my change in energy is constant, so the average is equals to instantaneous. So it's just 500 divided by 2, so it's 250 joules per second. We also have a special unit for power. Is if you want to be rigorous when just calculating the average, if you want to be if you want to simplify the unit, we have a special unit for it, is watts. Okay, so spelled watts, named after the scientist who did a lot of this work. And yeah, and that is one way you can go about it. Now, if you change that to going at a slope, the beauty of energy is it's also pretty simple, because if you, for example, don't care about friction, when you go up here, what's the energy change? And let's say if you walk at a constant speed, up the slope, what's the energy change? So here, the KE is 1/2 mv squared. Here, when you get to here, if you walk at a constant speed, KE equals to 1/2 mv squared. And here, the U is mgh, this is h. And here, the U is mg, I'm going to set this as 0, so mg 0, right? Okay, so what's the change in the energy. How much energy have you overcome? Well, the kinetic energy has no change, right? So the total change in energy is really just mgh, and you exactly get the same answer that way. If the height is the same, you have a different mass. You're not 5 kilograms, but you can directly see however many seconds and divide that by time taken. Okay, so it's basically a simple idea. There isn't too much to this. It's really the simple idea of the rate of change, how fast you're consuming and how fast you're generating or overcoming, so doing a certain amount of work, overcoming certain amount of forces, and how fast you're doing that. Okay, so in 3B, this is a much more useful concept with looking at how much power you can generate with power plants, with electricity, and how much power is stored. When you look at a light bulb, it says 100 watts or 60 watt. What that means, it's emitting, it's per second emitting 60 joules of energy. In that case, it's light energy, right? So when you look at the power of an electronic device, maybe an iron board, it's however many watts, you now understand it is however many joules in 1 second. It's giving out that amount of, so a light bulb would be emitting light energy, right? A speaker of certain watts would be emitting sound energy. And a heater, you can have a heater at home, right? And that's emitting heat energy at a certain wattage or power. Okay, so useful daily life concept, but very simple. If you look at the problems, very simple to apply. Yeah. So this concludes really our discussion on energy. Most of the main takeaway of this is really the power of it to, no pun intended, but the power of it to solve a lot of kinematics problem in a very efficient way, as an alternative to the Suvat way of solving things. And yeah, so this will nicely lead us into looking at collisions and interactions of things. We'll introduce the idea of momentum, and we can study much more interesting scenarios.